Okay, this section of notes is on using a normal distribution to approximate a binomial distribution. So let's start with a review question or a review scenario, and then we'll see why we want to use this normal approximation. All right, 63% of college students eat on campus. If a random survey of 30 students is conducted, find the probability that exactly 16 of the students eat on campus. All right, if you remember doing this, we used our binomial probability calculator feature. What we wrote is binom PDF. We had our n value, the number of students surveyed, the probability of a successful event, and then the number of successful events that we were looking for, in this case 16. And we ran that on our calculator, and it gives 0.081. On the second one, more than 20 students eat on campus, meaning 21 or more. What we had to do, or the way we did this, was we went into our calculator, and in L1, we entered 21, 22, 23, so on. Kind of a tedious process from 21 to 30. Then we went up to the top of list 2, and from there we ran our binomial distribution. N equals 30. What was that probability? 0.63. And then we used L1 as our X value. Paste that in. And we got those numbers, and then we took the sum of those numbers. The point of this being is we had to enter all these values into L1 and then run our binom PDF that we're seeing in all those for all of the numbers in L2, and then finding that sum that we did on the home screen. And if you remember that, it was sum L2 to get that probability of 0.277. So in L1, we had to enter all those numbers, 21, 22, 23, ... 29, 30. And then L2, we did our binom PDF, 30, 0.63, L1, and then sum L2, and we got our 0.277. Okay, so we had enter all those numbers into L1. All right, take a look at the next question. So again, we have 63% of college students eating on campus. Now we have a survey. There's 270 students for our n value. Find the probability that less than 162 of them eat on campus. So if you tried putting this in your list 1, you would have to start with 0, 1, 2, 3, all the way up to 160, 161. That is a lot of numbers to try to put in. Do you think your calculator could even handle that much data? Most of the calculators can handle a list that big, but to try to run that would be way too many calculations to do. What we will do instead is we'll use a normal distribution, and we'll approximate that using a normal distribution. So that's the reason why we do this, is because this would be much too long to put in our list L1. Okay. In order to use this normal approximation of a binomial distribution, there are 2 conditions that must be met. N times P has to be greater than or equal to 5, and N times Q also has to be greater than or equal to 5. And if you remember from the past, Q is the probability of an unsuccessful event, or 1 minus P, or the complement of P. When you are using a normal distribution to approximate a binomial distribution, there are a couple different things that'll be new. One of them is we have to use a correction for continuity, because a binomial distribution uses discrete data and our normal distribution is for continuous data, we need to do what's called applying a correction for continuity. So here is an example. All right, let's say we have the x value of 4, x equals 4. Okay, as you can see, that's placed on our normal distribution. The problem is when you're looking for a probability of this, you just have x equals 4. There is no area underneath the shaded region because we're looking at x equals 4, not below it, not above it, but for itself. So when you think of this, we have x equals 4. Down here we have x equals 3, x equals 2. Up here x equals 5, x equals 6, and so on. We want x equals 4, but we do not want to include 5, which is way up here, and we do not want to include 3, which is way down here. So what we do is we use the boundaries on 4. You should recall that from the past. The boundaries on 4, lower boundary is 3.5, upper boundary is 4.5. So we replace that x equals 4 with its boundary values. That is the correction for continuity. Now the data point down here, 3, would go from 2.5 to 3.5. The data point 5 would go from 4.5 to 5.5, and so on. Okay, you can see right here, when x equals 4, the correction for continuity uses the boundaries 3.5 and 4.5. All right, here's the next one, x equals 9. What are the two boundary numbers that are used here? And the two boundary numbers used when x equals 9 would be 8.5 for the lower boundary, 9.5 for the upper boundary. All right, for the next one, if x is greater than 10, okay, the way this might be worded in a scenario is more than 10. Okay, what is it? Probably more than 10 students eat on campus or something like that. Okay, so what does that mean? It means 11, 12, 13, etc., going up. Okay, so to pick the boundary, we don't want to include the 10. We want above the 10. We want to go that way. So we're going to use 10.5 and above. So the boundary number used here will be 10.5. See if you can do the next 3. Okay, for the next one, x is greater than or equal to 10. That means we want to include the 10 along with the 11, the 12, the 13, and so on. So we're going to use the boundary 9.5. 9.5 catches the 10 as we go greater than the 9.5. Okay, what boundary number do we use for x is less than 10? Okay, we don't want 10. We want the 9, the 8, the 7, and so on. So again, it's the boundary 9.5. Okay, you want x values less than or equal to 10. That means you want to include the 10 as you're going to the left. So you want to include the 10. So you start at 10.5 and work your way down. At most 10, as an example, would be 7, 8, 9, 10, but not 11. So there's our boundary, 10.5. Okay, try this last one. Okay, so again, looking at my number line here, we went from 13 to 17. We want 13, 14, 15, 16, 17. Okay, it includes them both with the less than or equal signs. So our boundary is there, 12.5, and right there at 17.5. Those are the boundaries you need to do the correction for continuity on these. There's going to be 2 formulas that we need. Okay, from back in chapter 5, we had mean equals n times p. We also have the standard deviation equals the square root of the product in PQ, or n times p times q. So back to the problem that we're working on. Okay, so first, does it meet the condition to use a normal distribution or a normal approximation? Okay. From the first page, There are your conditions. N times P and N times Q both have to be greater than or equal to 5. So let's test this one out. N equals 270. P equals 0.63. Q equals 0.37, or 1 minus the 0.63. Okay, so we have N times P equals 270 times 0.63. But you do that in your head really quickly, you get 170.1. N times Q is 270 times 0.37, which is 99.9. Okay, that's greater than or equal to 5. That's greater than or equal to 5. So yes, it does meet the conditions. These are greater than or equal to signs. Okay, they're both greater than or equal to 5. Okay, next step, find the mean and the standard deviation. Well, from our last page, we saw mean is N times P, standard deviation, N times P times Q, the square root of that product. Okay. Well, we've already found N times P right here. So the mean, I'm going to write N times P for the first one. times 0.63. The mean is 170.1. And on all of these, you'll already have the mean figured out because of seeing if this meets the conditions to be able to use the normal approximation. Okay, so there's the mean. Standard deviation is square root of N times P times Q, which is going to be the square root of 270 times 0.63 times 0.37. When you take that, do the product, square root it, we're going to round it to 1 decimal place, and we get 7.9. All right, the next step, find the probability of less than 162. Okay, we're ready to apply our correction for continuity now. So I'm going to give you a second to see if you can figure that out. What would be the value that we'd use, the boundary that we would use, so that x is less than 162? And we get 161.5. Okay. Now we are ready to fill in the values on our normal distribution. We know up here mu is 170.1 with a standard deviation of 7.9. This is our x value that we put on our normal distribution, 161.5. We're looking for less than that, so our shaded area is below it. And now we're ready to solve this thing. We want to find the probability, which means we're looking for an area. This is what we want to know. We're going to need a z-score so that we can go to our table. So z-score, as we know, equals x minus mu over sigma. In our case, it's 161.5 minus 170.1 divided by 7.9 gives us a z-score of negative 1.09. We know it's negative because it's to the left. So that assures us that we put these numbers in the correct order. Okay, we're ready to go to the table. We go to the table with a z-value, negative 1.09. We locate the area value associated with it, which is 0.1379. So that is our approximate probability that less than 162 of these college students eat on campus. All right, you go through the steps on the next one and see if you can get it. And then we'll discuss it together. All right, does it meet the conditions? Let's find out. N times P and N times Q. If one of these is less than 5, one of the products, then we know we're done, and it doesn't. We cannot approximate it with the normal distribution. 600 times 0.91 is 546. All right, N times Q is 600 times 0.09, which is 54. Both greater than or equal to 5. So yes, it does meet the conditions. Okay. Find the mean and the standard deviation. Mean equals N times P, which we've already found is 546. Standard deviation equals the square root of N times P times Q, which in this case is 7.00999. We're going to round it to 1 decimal place. So I have 7.0. We are now ready to apply our continuity correction factor for 540 to 550. I'll give you a second to try it, and then we'll see how it goes. To show from 540 to 550, we want to include 540, so we need to start down at 539.5, and on the upper end to include the 550, we need to go up to 550.5. Okay. We're now ready to fill those values in. We know our mean is 546. Lower boundary is our 539.5. Our upper boundary is 550.5. We're looking for the probability between those, or the area between those. Okay. We're ready to solve this. We need the z-score. I'm going to write z lower to show the z-score for the lower boundary. You can always pause this and do it yourself and then check back in a minute. And then the upper one take your z value to the table. And then to find our shaded area, .7389 minus 0.1762, 0.5627. All right, so what we found then, if 91% of households on a computer, in a random sample of 600, find the probability 540 to 550 own a computer. This is the approximate probability using a normal distribution to approximate a binomial distribution.